Yeah.
Hey everybody, welcome back to physics today. Hopefully we can get some videos out here. Today we're talking about electric current. Okay, so before we started talking about, or before we talked about static electricity, now we're talking about current electricity, which means it's moving. Okay, so electric current. Well, the first thing is a battery. Okay, so you guys know what a battery is? Well, first of all, have you ever seen one of these? It's a D. That's not a battery. That's a cell. Okay, so this is called the cell. And then a battery would be two or more of these in combination. Now you could have batteries in combination this way, where they're touching like that, and then like this, or you could have them in combination this way. Okay, now this is two different pieces, or two different ways to draw batteries. It's not in your packet, you do have to know this. Okay. Okay, so these are the two ways to attach batteries. If I attach both the tops and both the bottoms, and then I run it through some type of circuit, then this situation is called parallel. So these batteries are attached in parallel. And if you look at the battery, or if you look at each individual cell, you'll see that there's a plus on this side and a negative on this side. Okay, so if you're thinking of static electricity, electric fields, and stuff like that, this is really the same way. But the difference in voltage from the top terminal to the bottom terminal is 1.5 volts. Okay, so that's the volt difference per cell, and that's kind of the average alkaline cell. It's about 1.5 volts. Now, when they're fresh, they get up to like 1.6, and when they start dying, they'll get, down to, some of them I've had down to 0.09 because they were shorted out for a long time. So the total voltage difference, so if we're going to put a voltmeter across this piece right there, the difference, or the voltage difference, is going to be 1.5. Okay? When they're in parallel like that. But if we have our batteries in series, like this, then what happens is we have a plus, negative, and each of these batteries has a 1.5 volt difference from one terminal to the next. But you notice that they're arranged differently. So if we would take this out into a circuit, then we would not have anymore a 1.5 volt difference. But if we put a voltmeter on here, we would measure that voltage difference as 3 volts. Okay? So that's the difference between hooking up batteries in parallel and series. Okay, one will get more voltage, one doesn't. But the question is then, why would you ever want to do this? Why would you ever want to do that? Any ideas? Okay, so this is all, it brought up the alternating current, direct current nomenclature was brought up, and this is all direct current. So batteries are always direct current. They go in one direction, according to which way the battery is hooked up. Okay, so here's the deal. Let's say that you have a slide. Okay, so, and let's say that each slide has, a width of enough for one person to go down the slide at once. Okay? And we'll say that each slide is a battery or is a cell. So like a cell is voltage. Voltage is potential energy, right? Per charge. And just like a slide, when you slide down the slide, you have a change in potential energy per gravity, right? Or not per kilogram per mass, change of potential energy according to gravity, this is going to be the same thing. So when we talk about going down a slide, it's going to be like going from one end of the battery to the next. And that's when we use up our voltage, that's when we use up our energy. Does that make sense? Okay, so this is the battery slide for the voltage. Okay, so if we have them hooked up like this is the top of the hill, this is the bottom of the hill. Okay, how many slides do we have? 2, right? And they both, and one goes down this way, and the other one goes down parallel to that. Right? So like the change in height for gravity, this is 1.5 volts, or potential energy per charge, just like it would be like maybe 5 meters high. Does that make sense? And so these slides take you from the top of the hill to the bottom of the hill. Okay, so here's a question. How many kids can go down the slide at once? 2. So you can have a kid go down here and a kid go down here. Okay? And they both get this amount of energy per charge. Over here, though, we have a little different situation. In this slide formation, we have one slide on top of another slide. Okay? So notice the, what would be analogous to height in the gravitational potential. We have a further distance that how many kids can go down the slide at once? 1. It can go twice as far, but only 1 kid at a time. Okay? So, this here is, you get 3 volts as you go from, max to bottom. Here you get 1.5 volts going from max to bottom. So, this one you get a higher voltage. This one you get more kids, or we'll call charge, that can move per time. So each one of these cells has a maximum amperage rating. Okay, so amperage is the next thing we need to talk about, which we've already been talking about it, but we're going to extend that. So amperage is big I. Okay? And the label for amperage is A. So this is the symbol, this is the label, A is also called current. Okay? Okay, so 1 amp is like, 1 kilogram or 1 meter or 1 second. Amp is the name of the units. Okay? Okay, so what does this mean? Well, the mathematical definition is current is the amount of charge that moves past a point per second. Okay, so that's what current is. Q per T. Okay. Now, did we have current happening in our last chapter? Yeah, we did. When charges moved, that was actually officially current. The difference is between last chapter and this chapter is we force this current to stay on the wire, usually, or we try to, in the circuit. So let's look at this. If we have a wire, okay, so here's a wire. Okay. Now, a wire is made up of what? What are all things made out of? Charge, we could say, and neutrons. Because it's protons, electrons, and neutrons, right? So atoms is right, mass is right, charge is kind of what we want to think about now. Okay? So, there's these atoms that make up the wire, right? And they're all over. And the thing is, with metal, what do you know about metal and its valence shell electrons? It's very important. They're very loose. It's like loose skin. Remember we talked about that? So there's this negativity. Well, first of all, there's like kind of just the normal electrons, the ones that aren't in the valence shell of the atoms, and they're stuck in place. But then besides that, there's this kind of valence shell electrons where they're just kind of around, and they're kind of shared by all the atoms. So they kind of call it a sea of electrons, or they'll call it like the loose skin of the valence shell electrons. And so if I would bring a charge like this, you know what happens to these? They move, right? They would move away. That loose skin would move away. It would get as far as it can. Or if I did this, they'd all move further or closer. Okay, so what happens then is, and these electrons are moving, in all directions at all times. Because there's just so many electrons that they're all over the place. Now we'll talk about magnetizing electrons, and we'll talk about certain electrons moving in the same direction as the atoms and electrons next to it. And that'll be called domains, and we will talk about that. But for this part, mostly we can say that there's Brownian motion of the electrons, which means all directions at all times, basically, right? Or constant random motion. But if we put a voltage here, so let's say we put 12 volts here, and 10 volts on this side, there's going to be a movement of that charge, right? Now I'll tell you right now, the electrons are the things that move, which would be in this direction, right? According to the voltage, would be in that direction. But for physics, we don't use that. We use what's called conventional current. Because when Ben Franklin first started talking about this stuff, he didn't know about how the atoms were put together and which parts could move and not move. He said if there's more than normal charge, it's positive. If there's less than normal charge, it's negative. And he said that there's a movement from positive to negative. So this direction of charge, and more distinctly, positive charge moves from the higher voltage to the lower voltage. And all of our formulas are set up by this conventional current, which means going from positive to negative. Did you hear that? Okay. So we know which way the electrons are going to move. We know the protons aren't going to move because they're cemented into place, basically. Unless they're dissolved in a solution, then they can move. But in a metal, it's the electrons that move. But that's probably the last time I'll say that. Okay? So what happens then is we get an overall movement of current or charge moves on down the line. My question to you is, how fast do you think this moves in a wire? Okay, so it's completely opposite of what everyone thinks. This moves like in a typical car circuit. This charge will move about 1 inch every minute. Now, why does electricity happen at the speed of light is the question. Anybody? Because if I turn on the switch, it's on. I don't have to wait for minutes for it to get to the light bulb that I want to turn on. That's exactly right. Everything's made of charge. So if we have a battery situation, okay, I'm just going to draw this like this for now, and we take the wire, make it blue, okay, and then we have, a light bulb here, which I'm going to show you different schematics for this later, okay, and then we'll connect this. What happens, like say it's set, I'm going to draw like big dots so you get it, but of course there's, times 10 to the 23rd pieces in this whole wire. But if I have a charge here, everything is made out of charge, is what Sage said. And you guys agree with that, right? And if we have a conducting metal, every part of that conducting metal has loose valence electrons that can be shared. And they're basically, as close to each other as they're going to get, unless I'm going to draw these circles because they're inside the filament of the light bulb too, right? So when I turn this on, okay, first of all, there's a redox reaction that occurs. Do you guys remember what that is? So there's compound A and compound B on one side of the battery, and they're trying to get together, but they're too negative. So if they squirt out an electron, then they're not so negative anymore, and then they come together, and it's a compound AB. That is called an oxidation reaction. Okay? The reduction is easier to remember because when you add electrons, you reduce, right? Because it's more negative. So think of the reduction reaction. So then on the other side of the battery is compound C plus compound D. They're trying to get together, but they're too positive. So once they get an electron added to them, then they can get together as a compound CD. And that's called a reduction reaction because you added negativity to it. You add an electron to it. That's reduction. That one's easy to remember. The other one is the oxidation. And so those two reactions are happening inside the battery. One reduction, one around oxidation. And so what we do is we just slip in a wire and a light bulb or whatever we want to flow charge through, and we use that chemical reaction. And that's all that a battery is. So what happens then is charge, and we're going to talk about the positive flow, okay? So charge gets moved out of the battery. What happens to this charge? It gets bumped into, and that pushes that one, and 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 that, and each one pushes one, and over here charge moves into the battery because the reaction on that side needs charge, or this one needs to get rid of it. And so that's why it happens at the speed of light, because these are all basically connected like a train. If the engine moves, the whole train moves. Okay. When you get to your next physics, you'll talk about because there is, microseconds between each collision. So there is like what we call a transient process as it moves on down the line. But you'll talk about that in your next class. But for us, for right now, it all turns on at the same time. Does that make sense? So that's why everyone thinks that these electrons are moving so fast, because electricity happens right away, but it's not the overall movement. So, getting back to the beginning of our notes, current is the amount of charge that passes a point in 1 second. And 1 amp then, 1 amp is 1 coulomb per 1 second. 1 coulomb of charge passing a point every second. Okay? So these particles still kind of go in all directions at all times, but the whole group of them move on down the line as they're wiggling and jiggling in all directions. So the overall net direction is in one direction, even though each of them are also going all directions, just more, or in this direction more than any other direction. And that's current. Okay, so I got a question about it for you. If you have a wire filled with charge, where do you think the extra charge is going to go? On the outside, right? And I think that still holds true in circuits. I don't see it much in the textbooks, but I have heard people talk about it. Kind of one of the thoughts is that most of this extra charge or this electricity flow is happening mostly on the outside of the wires. So, I got a question with that in mind. If I have a wire, and this is a cross section, where would there be resistance to the flow of the charge? Why would there be resistance? Any ideas? Well, inside the wire, we have all these positives, right? And then we have all these negatives here too, right? So the Coulomb's force of those positives and negatives will be part of the resistance of the wire. Okay? So, I got a question. Do you think this wire or this wire would be less resistive? Yes, it's this one, definitely. This one has less resistance because there's more area of the wire, there's more places for charge to flow. You know what I mean? So if you think of a slide, which is more resistive, this slide or this slide? Which is more resistive? Yeah, so like this one you can have, people can go in multiple places kind of. It's a bigger area to slide down. This one there's one spot, so it's going to be resistive. And if you get overweight, you might not even be able to fit down that one, right? That happened to me. So, the bigger the wire, the less resistive. Does that make sense? Look at your battery cables in your car if you don't believe me. The big ones are on the battery, right? Okay, so if we talk about resistance of a wire, we can say that it's directly related to where would we put this now? And instead of circumference, we'll talk about the area of a cross section of the wire. Would that go on top or bottom? Where would that go? Yeah, that's inversely related, right? As the area increases, the resistance decreases. Okay? So have you ever gone down a metal slide in the summer with shorts on? What does that do to you? It burns your skin, right? What if the slide was longer? Would that be more or less resistive than the shorter one? Joe says more. Yeah. Yeah, so the longer one is more resistive because, you're, like on the side it's easy to tell you're going to be burning your skin longer, right? So that hurts, more resistance, more, blood and blisters and stuff. So where would that go? The length of the wire would be on top or on bottom. Okay, and then we have different kinds of slides. So one's plastic, one's metal, one's carbon fiber. How would we rate that? Let's say that the rating is, the bigger the rating, the more resistive. Where would that go? On top, right? I kind of gave that away. Okay, so with that said, I think we can come up with a formula for the resistance of any wire is rho L over A, and we want to double check that formula and make sure there's nothing else with that. Okay, so this is right. So rho then is just a rating per metal. So each metal is going to have a different electron affinity or attraction. Okay? So with that said, we'll kind of get back to our battery business. So here's your first AP formula, or your second one. First one was current, is charge per time. Second one is resistance of a wire, is rho L over A. But with this talk here, we want to get back to the idea, because we talked about rho, and rho would be different metals. So what Luis Galvani did is when he took his frog and he was scraping away part of the leg, right, here's the muscles, and he came down in with a scalpel that had a certain kind of metal on it, and he was scraping that away, and his lab table was made out of a different kind of metal. When he got this muscle thinner and thinner and thinner, he saw that that the strand twitched. One of the muscle strands twitched. And since muscle is made out, has a lot of salt water in it, it conducts electricity. Because if we have a solution, it can conduct electricity. So why did it conduct electricity? Well, because basically that metal had a different electron affinity than the metal on the table. And rho isn't electron affinity. I'm just saying, since we talked about different metals, since one of the metals is more attracted to the charge than the other metal, it actually, since it could go through that saltwater solution that was, around and inside the muscle, there was a transfer of charge that happened. And when that happened, it excited the muscle, and it twitched or constricted. Okay, so then after lots of different experiments, they came up with a couple different ideas. They had, it looks like a Petri head kind of, huh? With the salt water, and this is, the salt water, and they had salt water. And the first, one of the things that they did is they put like bimetal strips. This is one kind of metal. I'm going to touch, and then this was another kind of metal. And then they have the same situation over here. And there's a better oops. I don't know how that happened. That was the wrong color. There's a better picture in your notes. But they had the same situation over here. And they were able to tell that the current was flowing through this metal. And then a little bit more common to what we're doing today is they'd have like metal A, and then they'd have like a saltwater saturated cloth, and then they'd have metal B, and then they'd have that another cloth, and then metal A, metal B. This is pretty boring, huh? And they were able to tell when they attached these two together that they were getting charge flow through this. This is called Volta's pile. Volta's pile, and that's really the common battery. It looks just like that 9-volt kind of, doesn't it? Mm-hmm. And I guess they say that they've seen this stuff back in the Egyptian times, so Volta's pile would be like named after someone a lot later than the Egyptians, right? In time. Okay. So, any questions about that? Okay, so we're going to conclude this discussion. You guys work on homework number 1 for tomorrow.